Well, we're off and running again on there's echoing. Okay. And so thanks for joining us. I know from talking to a few of you that the series is, I mean, it has its challenges. And physics isn't something we all kind of think about very much, and that includes myself until fairly recently. So I understand that, but I think you'll find that some of the concepts, ways of thinking, will become more intuitive and more understandable as we go by. Next week is the wrap-up session, and we're not going to be talking so much about new material as exploring what we have learned, but also expanding things. One of the topics I want to bring up then is the nature of science and scientists, but some of you have commented on why these hominins started out each week. And I think the oldest one was 3.2 million years old, and then Neanderthals are figured in it. And today, Denisovan, which we'll talk about in just a second. But why? Well, the why is, when did our ancestors cross a threshold? Clearly, there was a threshold to cross when they began to be much more aware of their future, reflect on their past, even develop some kind of narrative or creation story about their existence and ask all kinds of interesting questions. My guess is that period was probably maybe somewhere around 100,000 years ago, might have been earlier in some vestigial form, probably linked to the acquisition of language as we understand it. But that's all stuff to be talking about. I mean, if you think about it, if you were an alien kind of cruising around Earth until fairly recently, up to maybe 200,000 years ago, there was no one down there, bipedal or not, asking these kinds of questions. This, in the 4 billion year history of life, that's a pretty recent acquisition. So that's something to think about, because there obviously is a trajectory to human evolution, and there's no reason why that trajectory wouldn't continue on. And if it did carry on, what would the implications be for our intelligence and ability to answer questions? I do think that there are cognitive limits to collective limits and personal limits to understanding some of the stuff that you've been dealing with in physics, but in other areas as well. So those are all questions that I want to get to. One thing I haven't mentioned before, I don't think, were any books. Well, a couple of people have asked me, and I'll just mention this one, 7 Brief Lessons on Physics by Karl Schwarzschild. It is a gem. He's a quantum physicist, works in Messier, and his current interest is quantum gravity, which we're not dealing with, but anyway, quantum gravity. But he has a gift for writing and making concepts clear. It's a thin book with a lot of interesting material in it. So that's one that's interesting. And then one of the Nobel Prizes this year went for gene editing, which I've been expecting now for 3 years, and it finally came out. And then I dug back in my library because I remembered that Jennifer Duda had done a great book, written a great book. She's a cracking creation. It's a wonderful thing. Because, think about it, this is the first time that humans have been able to change or will have the tools to change their own evolution with gene editing. That is a huge, huge change. And in parallel with that is artificial intelligence. So these are things to think about so those are big questions, and we don't have answers for all those things. But anyway, let's look at that first one. Isn't that a magnificent picture of the Milky Way? In the center of it, in that bright patch, it's bright because it's crowded with stars. So many stars that they overlap. The Milky Way, I mean, no one's counting them one by one, but there could, I mean, earlier estimates, maybe 100 billion stars like us. It's probably double or triple that. And so when you look at that and all those little dots and dots and dots on dots, isn't it incredible? It is absolutely incredible. Now, why that concentration? Why that white concentration of stars in the middle? Because of a gigantic black hole. Most galaxies have a huge black hole at their center, and this is one. So, and that's something we're going to deal with. And by the way, a Nobel Prize went for that one this year. So we're right on topic with the Nobel Prizes. So let's just move along. Now, getting back to that tradition, this is a Denisovan. It's an interesting thing in the last, say, 20 years. Started at the Max Planck Institute in Germany, but the ability to read archaic DNA and one of the species that was identified were the Denisovans in a cave in Siberia, and this young lady is actually from Tibet, but they were able to find DNA from a fingertip and a tooth, and actually recreate what she looked like. Isn't that an extraordinary thing? By reading the methylation of bases in this ancient DNA 160,000 years ago, they were able to come up with this picture of what she probably looked like. And it was quite predictive because in this prediction included what the mandible would look like. And in this case, that was all that was left. And there was almost a perfect fit between the real mandible and the one created from the information in her ancient DNA. Isn't that extraordinary? So, but one of my interests, as I said, is when did they cross that threshold? Well, to move on to the Nobel Prize this year in physics, Roger Penrose of Oxford, Reinhard Genzel, and Andrea Ghez. Roger Penrose he got the Nobel Prize for work he did in the 1960s. I mean, he jokes about it in interviews about getting the prize this late in the game. Reinhard Genzel and Andrea, they've done parallel studies. And by the way, they both have professorships at the University of California, but Reinhard leads a team in Germany, and using telescopes in Chile and Hawaii, they are the ones who have done the study of this massive black hole at the center of our universe. So that'll be part of the Nobel series. But it also, I mean, it's hard to talk about what's going on here without mentioning that. Well, I've already told you about. Now, how big is this black hole at the center of our universe? Well, 4 million times the mass of our sun. That's pretty big, and as big as our solar system. So that is a huge black hole. And so we'll talk more about that later. Now, gravity. Ever since Isaac Newton and his laws of gravity back in the 1600s, and then this revolutionary revisit by Einstein. But gravity is at the center because gravity really dictates the orbits of planets around the sun and the sun around the Milky Way. It plays a role in the earliest universe in dark matter, in shaping the earliest development of what will become galaxies and stars. It also, when stars begin to run out of energy, chiefly from hydrogen, they collapse in on themselves. And if they're large enough, some giant stars, they become black holes. And so gravity is the factor that leads to that gravitational collapse. But it also changes time. We don't think about that. And heavy masses, anything that's heavy, like our sun and our solar system, bends or shapes space and time around it. And finally, because it's part of the Nobel Prize, extremely heavy masses or very dense masses can fold in on themselves and create this black hole from which nothing can get out, or almost nothing can get out. So now I wrote a little piece in the local paper about this because this Karl Schwarzschild, in his first chapter, he says the title of the chapter is "The Most Beautiful of Theories," and at the very end, the last page of that chapter, there's the equation, and what does he say about it? He says that really it's the equivalent of the very best works in the arts. And so even though the equation looks like gibberish, to those who are able to read it and make sense of it and understand, at least in some way, what it means, it's huge, the implications. So the left side of that equation compresses all the information about the geometry, the shape of space-time, and how it's warped by objects. And then on the right side, in turn, how that curvature of space-time influences how matter moves. So there it is. We actually have 3 looks at this because Karl Schwarzschild, I've got my hands on that chapter here, he puts it this way. The equation describes how space bends around a star. Not only do stars orbit about a star, but light is bent around a star. We'll get to that in a second. That was the first evidence that general relativity was correct. But he also predicted that time changes too. And so we'll talk about that. I like this one by John Wheeler, a physicist, because this is the nuts and bolts of all of relativity. And let me tell you, solving relativity for Einstein was an exhausting task over 8-9 years. He wasn't the best of mathematicians. He had to heavily lean on friends and others who were more gifted than he. So when I show that single equation, that doesn't begin to tell the whole story. But John Wheeler sums it up. Matter tells space-time how to curve, and curved space tells matter how to move. It's a beautiful summary, isn't it? So, something about the implications of general relativity. Well, I've already said it. Space and time are linked. There are gravitational fields associated with dark matter. I mentioned that in the birth of galaxies and stars in the earliest universe. And they're also associated with the remnants of stars when they collapse. And the ultimate expression of that is black holes. So, well, now often it's illustrated this way. And space-time is like that net. And so we have a ball, Earth in this case, kind of dropped in this net, and the net is stretched. It's a popular way of illustrating it, and there's some truth in it, but it's also misleading because you have to realize that this is one plane. This assumes that there's one trampoline here, and you drop the ball in it. But there are almost an infinite number of trampolines in all dimensions around there that in this case, Earth would be changing. So for illustrative purposes, it's helpful, but just so you know, it's wrong. So implications of general relativity. Well, you know this from previous sessions, an expanding universe. And an expanding universe implies something very much smaller and very much smaller, ultimately the Big Bang hypothesis. We've already talked about gravitational lensing because, in fact, the first example, the evidence for that general relativity was true was based on an eclipse of the sun by the moon, right? And the light from behind the sun was bent around the sun, and Einstein's prediction turned out to be absolutely right. So the sun is a huge mass, bent light. The other one that we've also talked about, I think, in the second presentation was gravitational waves. Well, gravitational waves in what? A Newtonian universe never talked about what space was. It just seemed to be emptiness. Well, we know space is not empty at all. It's jam-packed with particles and various bits and pieces of energy, but it's also this web of a four-dimensional web, 3 dimensions for space, 1 dimension for time. So a 4-dimensional space-time. And anything cataclysmic, such as the merger of 2 black holes or 2 neutron stars or anything big, a black hole ultimately, the worst, can create waves, gravitational waves, or these ripples, if you like. It's the analogy that's often used is throwing a pebble out and see the waves kind of spread out from where the pebble hit the lake or the pond. It's probably more accurate to say, as an analogy, the ocean, and something disruptive happened somewhere within the ocean, and the waves spread out 360 degrees in all directions. That's more accurate. That's space. That's what I was trying to tell you about 2 or 3 slides ago. Time varies with the speed and gravity. And we're actually going to read a little tape of that from Bernowski's series in just a moment. And then of course, I'm repeating myself, I think, for about the 3rd or 4th time, that the greatest impact of general relativity is manifest in black holes. And what's been called a singularity. What's a singularity? Well, Penrose, really, and Stephen Hawking. I don't know that they coined the term, but or if anyone coined the term, it was probably Penrose. But it's a point of infinite density, whatever that means. Most physicists and mathematicians really hate infinities. The whole idea of an infinity. But certainly the idea of something incredibly dense. And of course, that was presumably, with the hypothesis of the Big Bang, where it all started, with a singularity, which has led some people to suggest that if a black hole could become large enough, it could birth a new universe, right? So that's partly where this whole idea of multiverses has come from. So something to think about, certainly gets the imagination going, doesn't it? Well, we're going to talk about how Einstein, in his first paper in 1905, that one of those 5 papers actually in 1905 was on special relativity, really talking about how speed affects time. So we're going to try this. We'll see how it works. But this is from the Brodowski series, and this little clip takes place in Bern, which is where Einstein worked in the patent office, the tram, and the clock. So I'll let Brodowski kind of describe this to you, and you see whether you like it or not. I think it's a marvelous piece. So off we go. All right.
Okay.
Okay. Can you hear me? You can hear me? Okay. Well, that was some ride. I didn't think we'd get through that. You know, it's something I had to watch about 5 or 6 times before it sunk in. But visually, it really does give you a feel for what happens to time. And if you just said that, if you just say there were 2 synchronized watches, one at the station underneath the master clock, and the person, Brodowski, sitting in the tram, then at half light speed, Brodowski's watch, or the time, would have been inflated, or time gone much slower, maybe by a factor of 1/3 or more. That's real. As is the kind of change in space. You saw the people outside kind of becoming narrower and taller and thinner. So these are real phenomena. Do they make a big difference? Certainly not on Earth, because we don't travel anywhere near fast enough. And probably not for landing people on Mars, because the speeds of even the best spacecraft now, there probably wouldn't be much of an error between Newtonian physics and the use of Newtonian physics and general relativity to predict their course and to make a safe landing on Mars. But at these high speeds, at the kind of the speeds of light in space, and masses distorting. No, what's happened? Can't move this. Yeah. Now this one I did talk about, but it's a gravitational field of a massive object. And this gravitational field outside of it. And there's another sun in this case, which is unseen or blocked by this massive object. But because of the light from that position of the source, when it reaches the gravitational field, it's bent, it's lensed, so that someone on your right here can actually see the source. So that's very good evidence. And I should also say that time is slowed. Not only is time bent around there, but time is slowed in that transit around that gravitational field. So that's what's happening. And on the numbers, it's right. We've dealt with this one before. Now let's move on to black holes, because this gets us into well, the Nobel Prize. I was surprised to learn that the whole idea of black holes was as old or was much older than I thought, because there were 2 people, John Mitchell, a British philosopher, and Pierre-Simon de Laplace, better known, but both reasoned that heavenly bodies, if heavy or dense enough, um, could create the conditions where light could not escape. And so that's the beginning of the whole notion of a black hole. Now, there's this interesting character, Karl Schwarzschild. Albert Einstein presented his material on general relativity in late 1915. And it was revolutionary. Well, one fellow who caught on to it was this Karl Schwarzschild, and he was serving in the German army in Russia. And he was there to help them direct the trajectory of artillery shells. But in between that job, he was a great mathematician. He found some time to calculate the gravitational fields around objects in space. And he came up with this idea that if there was enough mass and it was compressed into a small enough space, how much? Well, if you took the sun and reduced it to something with a radius of, say, 2 miles, or if you took the Earth and compressed it to a radius of 1/3 of an inch, that's a pretty dense Earth, isn't it? And that's a lot of compression. But if you did that, the gravitational force would be so strong that no energy, including light, could escape it. So he told Einstein this, or at least he sent the stuff by mail to him. And Einstein congratulated him on his math, but said, well, he thought that was very unlikely and to be the case, but he appreciated the man's effort. And well, it turned out that as with a few other things that Einstein was wrong about, he was wrong about this one. So, well, what about black holes? Some of them are massive. The one that I mentioned in the Milky Way, some of them are much bigger than that. The intermediate ones, remember there was a slide that back in 2015, a group that was looking for gravitational waves detected gravitational waves from the collision of 2 black holes. Both of those black holes were around 20 to 30 solar masses, so in the intermediate range. And some much smaller. But theoretically, at least, it's possible that black holes could be really tiny, almost quantum sized or atom sized. So that's an interesting thing. Now, through all of this narrative, through Stephen Hawking's lifetime and Penrose's, I mean, the two men were friends and collaborated. But as Stephen Hawking said, kind of jokingly, but that all he needed to get a Nobel Prize was proof that black holes actually existed. And for all this period, they were theoretical constructs. And then last year, one was actually observed. And there it is. And if you're wondering why it's so fuzzy, it's because it's from a long, 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 long way away. This is a giant. This is a gargantuan one. This is probably maybe 1 billion sun masses, huge. Now, what the curiosity, I mean, there are two things about this black hole. One, it exists. So here's proof that they existed, that they exist. And second, its symmetry was very consistent with general relativity, and it's general relativity that predicted the existence of black holes. So physicists looking at this said, gee, Albert was right. And we don't need to talk about that, but Penrose's big idea in 1964, the thing that he got the Nobel Prize for was, well, you know, what happens? What happens to matter? If we fell into a black hole, what would happen to us? Would we just continue spinning down to the bottom, or would we kind of be shredded into our elementary particles, or would we be cooked on the way down? Well, of course, no one knows about that, but certainly something happens at that event horizon, that threshold. But what is it that concentrates all of those things? And Penrose's big idea was that the composition of the black hole is such that no matter what the curvature, whether it's outbending or inbending, all of the radiation that gets into that black hole, anything that gets into it, is concentrated and eventually finds its way to the singularity that I mentioned earlier. So that was his big idea. In 2 sentences, I've really condensed pages and pages and many pages of math. But that's the principle. And so he richly deserves that. And I think, isn't it interesting that Penrose, here's the Nobel Prize. I mean, they probably, Stephen Hawking and Penrose would have received a joint Nobel Prize had Stephen Hawking survived this time, but unfortunately he didn't. So I'm not going to get into that because that's Penrose's diagram. We'll deal with that in the Nobel series. Now, what don't we know? Well, under the but. Well, one of the extraordinary things about it, general relativity certainly predicts the genesis or the birth of black holes because it's the most extreme example of a mass and the gravitational field around it. But the problem is that beyond that event horizon, general relativity breaks down. It no longer holds. So what's actually going on? And of course, that's where people like Carlo Rovelli come in, because they're quantum physicists. And their speculation is, no one's visited in this middle of the black hole, so let me caution you that we don't actually know, but it becomes a quantum world. There's a transition between general relativity and the rules that govern quantum mechanics. Which leaves us with the challenge. Gee, here are the 2 great hypotheses of physics in the 20th century: general relativity and quantum mechanics, but they seem to live in different universes, so to speak. Are they both right? They seem to be both right and very predictive. So where's the common ground? Where do they actually come together? And to the best of my knowledge, we don't know. And there's lots of speculation about that. And you'll find some interesting information on the Nobel site for that. Now, onto this business about the giant black hole and the Milky Way. I'm going to try another thing. I don't know how well that worked out for you with the Brodowski one, but one of the great sources is the New York Times. They have great short video clips. They must have a lot of money because to create these things, they've done a beautiful job. But here's a short clip from, well, last week's New York Times. And on black holes, the nature of black holes and the formation of black holes. We'll see if this works. Otherwise, you're left to my explanation. So you can hear me? Well, I'm sorry about that experiment. This is all a trial because because with the Nobel series, there's such good material out there that we have to find a way of doing this, because I mean, it's all about visualization. Wasn't that Bohr and Einstein? Wasn't that their great gift beyond the math to actually see in their head, in their mind's eye, what might be going on? So anyway, well, just there's the Milky Way, and Sagittarius A is that singularity at the center of the Milky Way. Okay, can you hear me now? I hope. Anyway, the point I was trying to make was that Reinhard Genzel and Andre Gens, they faced enormous challenges. They are the experimental physicists of today. This is a 3-decade venture, just like the gravitational wave one was, meaning they needed continued funding and a lot of money to do this from various governments. So that was extraordinary. The other thing is, I mean, they faced all kinds of challenges. One is how do you track stars at the center of the Milky Way when you've got a 100-kilometer thick atmosphere, and that atmosphere, I just know this from flying, that you have bubbles of air, some of them warmer, some of them cooler than the surrounding air, but they act like lenses and they kind of blur images. And so they created virtual contact lenses to correct those distortions. And there are a whole lot of problems that they had to solve, technical ones, but what they were trying to find and what they found was that any stars close enough to this giant black hole, their orbits or trajectories would be influenced by the gravitational field created by that black hole. And that's exactly what they found. So they tracked almost 30 of the brightest of these stars, made it easier for them to see them if they were brighter. And some of them were just zipping like crazy around this black hole. And so wherever this busyness was and these distorted orbits was indirect evidence of where the black hole was. Actually, I thought last year we would actually get a picture of this black hole at the center of the Milky Way, but there's a lot of other stuff in between. Anyway, they deserve a lot of credit for this achievement. This is what I would call a technical engineering achievement, a first-class achievement at that level. This is not the kind of imagination that goes into what Bohr and Heisenberg and Einstein were doing in the early 1900s. This is quite a different thing. I'm not making a value, I'm just saying they're different. And the gravitational wave stuff was very much the same way. And yeah, well, there's that merger of two black holes. and a merger of neutron stars. And I mean, the literature's stuffed with these simulations of, and in this case, of these gravitational waves. And I'm not going to get into that, but this is what I want to get to next week. And if you have some other suggestions, get a hold of me. By the way, there are some questions that several of you have asked, and I hope to answer them if I can next week. But what I would like to do in the wrap-up session, subject to whatever you want to add to it, is to talk about the nature of science. That includes the relationship of science to art, science and creation stories, and if you like, religion. And because I'm of a certain age, and because of my neuroscience career was in part related to this question of what happens with aging to nerve cells, what about the relationship of productivity and creativity to age? Are they related? I'm certain they are, but we'll talk about that. And just while we're on that last subject, physicists, mathematicians have a short shelf life, meaning they do their best work in their late teens and 20s. Physicists, you can add another, for theoretical physicists, you can add another 5 or 10 years. Penrose did his stuff in the mid-1960s. And that was brilliant theoretical work and math. So it's an interesting thing. Now, there are all kinds of outriders for that. So that's what we're going to talk about. And then we'll move on with a week's rest to the Nobel Prizes. So I hope you're on board for those, because I think if this were wine, this is one of the best years for a Nobel Prize, at least in the sciences. I can't speak to the Peace Prize and the Economics Prize. I thought that one on the surface was a little weak, but we'll see. I was intrigued by the poetry, prize for poetry. That looked promising. So all the best to you. And it's been a quick ride, hasn't it, through these 5 weeks. But I think next week could be the most interesting of all. So just bring your imaginations along, and we'll move along. And we'll see you next week. Bye-bye.